to the cloud.
Hi, everybody. Welcome. Thank you for joining us for the first high energy astrophysics seminar of fall 2020. We're already at fall. Sorry, my computer's pinging, so if you're hearing random noises, I'm sorry about that. So as we normally have, this seminar will be on Wednesdays through the semester at 12:30 p.m. Usually we'll have two speakers. I think we have one exception this time where we have one 1-hour speaker. And yeah, we can go ahead and get started. Please hold your questions until the end of each talk. And at the end of each talk, you can either raise your hands here or put your questions in the chat or put your questions in the Slack channel that we have created for this. Okay, so without further ado, I would like to introduce to you Yuanyuan Zhang, who is our first speaker. She completed her PhD in physics at the University of Michigan back in 2016 and is now a Schramm postdoctoral fellow at Fermilab. She spends most of her time working with the Dark Energy Survey and LSST. She mainly studies galaxy clusters and has done a lot of work with them, both in optical and X-ray. She also has a lot of interest in writing software and burns up a lot of time on computing clusters to process optical images. She's also on the job market, so something to keep in mind. And today we'll be talking to us about some of her work with clusters. So Yuanyuan, take it away.
Thank you, Rutu. So start screen sharing. Can you see my screen okay? Yes?
Yeah. Yes.
Okay, great. Thank you. Thank you. So this is definitely an honor and a privilege to be invited. And I also want to spend 20 seconds acknowledging, my privilege in the middle of a pandemic, racial injustice, unrest, and also natural disasters. I understand that many people have not been able to peacefully work these days. So my talk today is gonna be about doing low surface brightness studies with optical photons with the Dark Energy Survey, and especially the diffuse low surface brightness light in galaxy clusters. So all of the all of the work I'll be mentioning today are all based on the Dark Energy Survey data. So here I just want to give a brief overview. So the Dark Energy Survey uses the ground-based Blanco telescope in Chile. It is a wide field optical imaging survey in 5 bands, and its goal is to image about 5,000 degrees squares to the depth of 24 to 25 magnitude. So the Dark Energy Survey, or DES, is not the widest or the deepest survey on the market. But given the combination of both the area and the depth, it is widely recognized as one of the leading surveys, optical surveys in the pre-LSST era. The primary goal of the Dark Energy Survey is to study dark energy through large-scale structures, as well as type 1a supernovae. But like most of the large-scale structure surveys, DES has also proven to be a quite successful discovery machine for any astronomical topics. For example, people use DES data to study Milky Way satellite galaxies and also to do optical follow-ups of gravitational events. And there's also quite a bit of studies to do galaxy evolution works, which is what I will be talking about today. I also want to mention that the full data set of DES has already been collected and processed and will be made public in early 2021. So all of the works I'll be mentioning today, I expect the raw data to be available early 2021. So if anyone is interested in doing these works, I would be really excited to see what the community finds. So a primary science subject of DES is galaxy clusters. So here I'm showing the image of the bullet cluster in the DES data, full depth data. So most of the clusters in our full depth data will have details like this image here. Generally, DS expects to find most of the galaxy clusters more massive than 10 to the 14 solar masses in our data. So expect a high completeness, high efficiency for any clusters above this mass threshold in our data. In total, we are finding about 30,000 clusters all the way to redshift 0.9. The primary science goal is to use these clusters to constrain dark energy through cluster abundance. But we have such a good sample, then it could also be used for any astrophysical studies. And in my talk, I'm using them to study the diffuse light inside galaxy clusters. So taking a closer look at this bullet cluster image from DES, there's a lot of yellowish galaxies in these images that are the bright galaxies, that are the cluster galaxies. And in the center of this cluster, there are two very bright galaxies. So these are generally recognized as the central galaxies of the clusters. So bullet cluster is a bit special that there are, a couple of galaxies with comparable sizes and luminosities. So you are free to pick your favorite here as the central galaxy of the cluster. But regardless of your pick, I hope that you will notice that around these two central galaxies, there's some fuzzy diffuse light around them. And they are most obvious between these two central galaxies, kind of as a low surface brightness bridge connecting them. So this kind of fuzzy diffuse light is very common in the images of galaxy clusters. They are generally referred to as the diffuse intracluster light, or ICL. This kind of light is actually first, some people say that it's first noted by Zwicky back in 1951 when he was looking at the images of the Coma cluster. At that time, he referred to it as the luminous intergalactic matter with extremely low surface brightness. So at that time, he already acknowledged two things of this kind of light. First, it does not belong to any galaxies, it's intergalactic. And second, it has a very low surface brightness level. So also I want to note that this kind of diffuse intracluster light is different from another very popular topic these days called ultra diffuse galaxies. These ultra diffuse galaxies will show up as low surface brightness galaxies in images inside galaxy clusters. But that's not what I'm talking about today. I'm actually talking about this diffuse light that are not galaxies and don't obviously belong to any galaxies other than being attached to some central galaxies. So this is the intracluster light. Now, moving on, the existence of intracluster light is not surprising at all. So if you look at the galaxy interaction processes, either a minor merging event or major merging event, there's a lot of stars that are being thrashed around in this merging event. Or sometimes there's also stars that are being formed that are very far away from the galaxies. So generally, we should expect that some stars kind of get thrashed around when galaxy clusters form and experience a lot of interaction. So, generally we just expect that there is some diffuse stellar component around the galaxies and inside galaxy clusters. Now, with that kind of thrashing, diffuse intracluster light in the end could potentially make up a very significant component of a galaxy cluster stellar content. So here I'm showing the modeling results from Boruzzi 2013, who was modeling the universe global star formation rate and also the global galaxy merging history. So here is the modeling result from him about the galaxy cluster stellar distribution. The green line here is the stellar mass of the cluster central galaxies. It experiences rapid growth in the early days of the universe before redshift 2. And then in the current days would have reached a total stellar mass of about 10 to the 11th solar masses. So it's a massive galaxy. Intracluster light, on the other hand, in Bruce's modeling result, turns out to be an even more massive component than the central galaxies. So its total stellar masses is about 8 times 10 to the 11th solar masses. So that's about 4 or 5 times more massive than the central galaxy itself. So it could be really significant. So I would say it could be really significant because so far observers and theorists haven't agreed on how significant this component is. So observational studies so far, they reported the values of diffuse intracluster light in the total cluster data content. What is a fraction of that light? So far, they've reported values anywhere from 6 to 60%. So it could be a minor component, or it could be a dominant component. And the reasons these values vary so much is because it's very hard to do, and the methods people use vary a lot. Simulation studies, on the other hand, has better agreements. So the reported values usually fall between 20 to 60%. And in these days, it seems to be stabilizing between 30 to 50% in the newest simulations. So there is some good news that simulation seems to be figuring out this these days. With intracluster light potentially being a very significant component of galaxy clusters, not considering intracluster light when studying galaxy evolution in clusters is generally not a good option. Ignoring intracluster light or not considering them in simulations because people lacked the observational constraints have caused some serious tensions in galaxy evolution modeling. Here I'm showing an early simulation from the Lucia 2007, which is a semi-analytical simulation. There wasn't good constraints on intracluster light content at this point, so it was not included in the simulation. In the end, the simulation predicted very rapid growth of the cluster central galaxies since redshift 1. And then when observers look at it, we find the growth to be relatively mild. And for a while, it was a big source of tension in people that study cluster galaxies. And eventually, we realized that we're probably ignoring too much intracluster light, that the gap could be explained by a significant intracluster light component. So this was the case with the cluster galaxies. I also want to note that a similar tension existed with the luminous red galaxy evolution in general, and there the diffuse light was also considered to be a possible explanation. So here I hope I have made a case that there is diffuse intracluster light in galaxy clusters, and it could potentially be very interesting, and therefore more observational studies about them is needed. So why haven't astronomers jumped into these topics yet? Well, that's because a lot of people really want to, but there are very significant challenges facing observational studies. So the first hurdle people need to overcome is that in order to study low surface brightness light, we generally need very long exposure time on very large telescopes. So here I'm showing the result from 2014 that studied intracluster light in one galaxy cluster at redshift 0.4. This study uses about 2 or 3 hours of exposure time on a 12-meter telescope. And in the end, they were able to measure intracluster light, which are the green colors in this plot here, to about 26 magnitude arcsecond squares. On the other side, this is the radial extent of the measurements from the authors. So with about 26 magnitude arcsecond squares, or if you go a bit deeper to about 28 magnitude arcsecond squares, they were able to measure intracluster light to about 150 kiloparsec from the cluster center. And we know that intracluster light actually goes a bit further. So despite the feat achieved with this 3 hours of exposure time, we know that we need to be going much fainter. And that means much longer exposure time. And if you happen to have a smaller telescope that is not 12 meter, 4 meter, or 8 meter, if people are really lucky, that means the exposure time will really exponentially increase for studying intracluster light. Even if people have got access to a lot of exposure time on large telescope, there's significant challenges in the data processing to study low surface brightness features. Sky background in optical images is very high and is much higher than the low surface brightness features we are looking for. So the sky background subtraction needs to be done with a lot of care. One common problem that one common approach is that in order to account for the spatial variation of sky background, people model the background with relatively small scales. And with some small scales modeling, when we get too close to the bright objects, we tend to overcount the sky background, and in the end, over subtract all of the low surface brightness features we are looking for. So that will not be good. Another alternative is to not use small scale modeling at all. For example, in my work, we estimate background over the whole 3 degree squares field of view, which is really, really large. But the issue of this is that you deduce a lot of small scale light, and in the end, you need more photons and more fluxes to measure intracluster light. Even if you have done everything completely correctly, the bright objects in the images, for example, the bright stars and the bright foreground galaxies, they will again leave some contaminations because point spread function has extended features. So they will leave some residual light in the images again, which again interferes with low surface brightness light. So this is really just one hurdle after one hurdle and after one hurdle. But before this talk gets too depressing, I want to say that there is some easier approach in studying intracluster light, and there have been people overcoming, all of the difficulties in previous works. So one easier approach of studying intracluster light is to stack or average together the measurements of a bunch of clusters. So we will first, prepare or process the images of individual galaxy clusters, which could have, a lot of different signal to noise levels, like this one, which is better, and this one, which is a bit less smooth. And then we mask out all of the foreground objects and background objects we can see in these images. And then we take together these images and stack or average the fluxes inside them, and eventually create a detection image that is like this, that we can use to find low surface brightness light. The advantage of this approach is that it would average out all of the contamination features or the sky background fluctuations, evenly. So eventually you can just subtract a relatively even background. The downside is that you will need a lot of clusters in order to do this kind of stacking and averaging. But fortunately, with optical, wide field optical surveys like dark energy survey or LSST, we do have enough data to do this. I also want to mention that this method is first developed by Stefano Zebatti in 2005. It then faced a hibernation of about 15 years because of all of the technical details and the lack of data. But we were happy that we could develop the methods again with the dark energy survey data. So skipping 1,000 words on how we did all of the measurements, I want to start showing you some results now. So here is our measurements of the surface brightness level of intracluster light in about 300 clusters as a function of radius from the cluster center. This includes both the BCG and the intracluster light. Each black line in this image is a single galaxy cluster. And then the red line is their stacked or averaged surface brightness profiles. So with individual clusters, because of the depth of DS data, we can study, the BCG and intracluster light profile to about 50 to 100 kiloparsec. But that's really, quite small compared to the full extent of intracluster light. But after stacking together 300 of them, we were able to detect intracluster light to a surface brightness level of about 30 magnitude arcseconds squares at redshift 0.25. And that extends to about 1 megparsec from the cluster center. So it was one of the deepest studies done about intracluster light. With that kind of radio extent, going back to the original bullet cluster image, that basically means that we have detected the intracluster light, this extremely low surface brightness light, all the way to the edge of this image. So that's definitely beyond what we can see on the, visible level. So we are really happy that, with a lot of the data, we were able to mine this kind of details out of these images. Now looking back at the intracluster light surface brightness profiles, so we found that the BCG and intracluster light will need to be described by 3 surface profiles. So the surface profile is a model that is popularly used to model the galaxy surface brightness. Usually a galaxy is modeled by 1 surface profile, but we found that the BCG and intracluster light needs to be described by 3 surface profile. There is a core component, mostly the BCG itself, that extends to about 20 to 30 kiloparsec. This core component is rather steep and has a surface index of about 4. Outside of 30 kiloparsec, a stellar profile starts to take over. So I named that the envelope profile. The profile is shallower with a surface index of about 2, and it goes from about 30 kiloparsec to about 150 kiloparsec. So it is quite extended itself. And then beyond 150 kiloparsec, there is a third component that is even shallower. So I call that the diffuse component. It has a surface index of about 1 and effective radius of about 2 megparsec. So it's really very shallow and very extended. But the light contained in the third component is comparable to the light contained in the second envelope component. So an undergrad worked with me also went to just look at the normal red galaxies in the universe. There, the result looked very different from the central galaxies inside the galaxy clusters. He found that the normal red galaxies in the universe is actually very well described by a single surface profile here. There's some extra light, but that's really only 10% of the total light. So it's almost ignorable. So normal red galaxies look very different from the BCG and intracluster light inside the galaxy clusters. So there's something magical about the galaxy cluster environment that resulted in the intracluster light formation. So going back to the bullet cluster image, this also means that there is a core at the center of the cluster that is the BCG that goes to about 50 kiloparsec. Whatever we have seen at the beginning, there's some diffuse light around the central galaxies. There is a second component that goes to about 150 kiloparsec. So it's an envelope component. And then finally, there is a third component that goes to about 1 megparsec that is very extended. So coming back to the question of diffuse light being a very significant component of galaxy clusters, we looked at their integrated luminosities, which is the red line here. So it does smoothly integrate over the whole 1 meg/sec range. We also compared the intracluster light to the diffuse, to the satellite light inside the galaxy clusters. So anything but the BCG and the diffuse light. It turns out that, you know, they are the dominant component of the cluster stellar component, but intracluster light and BCG in total still makes up about 45% of the total cluster stellar content, plus minus 17%. So the result agrees really well with the cluster, with the simulation study, although a bit on the high side compared to most of observational studies. Let's see. So I would say one of the main conclusion here is that, you know, galaxy merging and galaxy interaction can be really messy, and there is a lot of component that is throwing around in the merging and interaction process, and it definitely should be accounted when surveying the whole, you know, stellar content of galaxy clusters. So how much time do I have left now?
I think you're just near the end.
Okay, so I'll wrap it up now. So here, before I conclude, I want to mention that all of the results so far are based on the dark energy survey data. DES turns out to be really good for studying low surface brightness light, but there is something coming that will be greater. So the area of LSST is about 4 times larger, and the depth of LSST is 10 times deeper. So in the end, I expect LSST to give us 40 times more photons and flux, and also improved algorithms to work with. So the next decade could be a really exciting time for studying this low surface brightness diffuse light. And to conclude, I want to say that we've published a few papers based on our intracluster light work, including comparison to lensing, you know, luminous red galaxies. The data used for all of this work will be public early next year, and we are also trying to make, you know, any of the paper products from this data available. So if people are really interested in comparing their diffuse light results to us, I would be really happy, you know, to provide our data products or to collaborate. So thank you.
Thank you. Are there any questions? Okay, I'm seeing some hands go up, so I'll call on people as I see the hands. And again, feel free to put questions in the chat or in the Slack room as well, in the Slack channel as well. So first, Giovanni Fazio?
Yes, do you know the spectrum of the intergalactic light?
So I don't know about the spectrum of the intracluster light. We generally only analyze, so because I work with imaging data, so I look at the colors. They are actually very consistent with the normal red galaxies, you know, inside the clusters. So I think spectrum-wise, I expect them to be relatively old stars.
Would it be, is there more advantage to doing this in the infrared rather than the visible?
So I think that would be really interesting because there's probably less contamination, but I'm not sure if anyone has tried that because there hasn't been a lot of infrared data that is suitable for this purpose, but I think that would be really interesting.
Mm-hmm. Okay,
especially with W1st coming up, you know.
Yeah, okay.
Thank you. Next hand I think I saw go up was Anthony Stark.
Yeah, I have a quick comment and then a question. So the quick comment is another telescope that will be really great for this kind of thing is a piece of giant Magellan, because giant Magellan consists of 6 off-axis 8-meter telescopes. So having a completely unblocked aperture for an 8-meter optical telescope is really the way to go for some of this stuff. And my question is there a motivation for the 3 components that you fitted to the diffuse light, a theoretical motivation?
So no, there's no theoretical motivation. So I think I did it. It's really a gradual approach of like, we fitted 1 component, sausage component, didn't work. 2 component got better, but then we fitted 3, which seemed to work the best. So it was not motivated by theoretical, theoretical aspects, but we did look at the simulation extension of diffuse light, like, what intracluster light looks like in simulations. It was also very extended. So in terms of the extendedness, they seem to agree rather well there. Hope that helps.
So maybe it's just one distribution. It's just a long-tailed distribution.
Yeah, that is possible. I mean, I would say that there's definitely actually, I think there's some evidence of a break somewhere around 100 kiloparsec, because we compare that to lensing, and it turns out that it follows lensing really well at a very large distance, but not so well in the center. So there's probably some dynamic difference, around about 100 kiloparsec. But so far it's purely data, data driven. So I haven't looked at the simulation or theoretical prediction yet.
Okay, thank you. In the interest of time, we'll take one more quick question. And then if anybody wants to keep discussing, I know Yuanyuan's schedule for the rest of the day still has some open slots. So you can feel free to sign up there. The last question, I know this popped up in the chat, from Stephen Wilner: what fraction of cluster light is in the BCG?
It's a very small fraction, so we'll see more like about 10% only in the BCG itself, and then another about 30% in intracluster light. But please also, there's large error bars involved in that, so it could fluctuate, a bit. Hope that helps.
Okay, thank you very much. Thanks, Yuanyuan. Thank you everyone for questions. I'm gonna hand it over to Peter now to continue.
All right, our next speaker is Andrea Travascio. Andrea is a recent graduate of La Sapienza, University of Rome, where this past January he completed his PhD thesis entitled Communicating Energy, Accretion Properties and Feedback in AGN. And during that time, he's worked at INAF Roma. Upon completion of his thesis, he was scheduled to join the Fabiano group here at the CFA, but the international travel situation has not been cooperative. So he will be at Trieste until this travel situation improves, and he'll be collaborating with us remotely. He's an expert in AGN feedback, mainly studying it via IFU observations. And his talk today is connected to his thesis work. Since he is moving, we don't have set slots for his Zoom visitor schedule yet, but you may wish to either email him or us directly if you're interested in arranging a meeting. And one more note for anyone who's interested, we have a couple more slots for 2 weeks from now. So please contact us if you're interested in speaking. With that, Andrea, are you ready to begin?
Yeah, I share the screen. Okay, you see my slide? No. Okay. Did you see my presentation? We
see it, but it's not in full screen mode.
Yeah. Okay. Okay, first of all, thank you, Peter, for the introduction and for this opportunity. I'm here to present you the work that I published during my PhD about the study of the circumgalactic medium around a hyperluminous quasar at ratio 3.6, finding presence of outflows and metals in there. So let me start a brief introduction of the CGM. What is the CGM and why we are interested to study it? First of all, the CGM is a diffuse and cold gas, and cold I mean temperature about 10 to 4 Kelvin, within the virial radius of the dark matter halo of a galaxy, typically around 300 kiloparsec. And we are interested to study it because we believe that it plays a crucial role in the so-called AGM feeding and feedback cycle. In particular, it could be venue of these processes involved in the galaxy evolution. Most of these processes are well represented in this picture by Tumilson et al. You can see here a galaxy with an active nucleus, with the interstellar medium gas, which is a accreting gas. Then we have outflows with different fates, circumgalactic medium, and then intergalactic medium, which is less dense gas beyond the virial radius of the galactic halo in this case, and distributed along filaments according to the cosmological simulations. And in this scenario, we know that we believe that this gas accretes the galaxy, triggering star formation, triggering supermassive black hole growth, as well as AGN phase. AGN and star formation can power winds, which hates the interstellar medium gas, sweeping away the gas, and probably plays a crucial role in this local star formation activity, and also in to stop the supermassive black hole growth until a new cold gas create starting a new episode of the AGN. And this is the reason for which we call this scenario a cycle, like a cycle. Part of these outflows are different. These outflows can have different phases. Part of them cannot able to reach velocity escape of the galaxy, therefore they rain back into the galaxy like resucking gas. While we think that part of these outflows can interact the circumgalactic and intergalactic medium, injecting energy, entropy, and metals in there, and altering the properties of this diffuse gas. In particular, all this set of processes produce a very complex and nonlinear correlation between the nuclear activity, host galaxy properties, and circumgalactic medium properties. Therefore, we want to study this very complex correlation. And to do it, we need to investigate, to explore the circumgalactic medium surrounding active galaxies. And to do it, we exploit the emission of this gas. Most of this gas is hydrogen, therefore we can observe, in particular, its Lyman alpha line, which is the most powerful transition expected in this case. The main mechanism able to to trigger this emission is the fluorescent, the case in which ultraviolet photons, ionizing photons from the central source, photoionize the neutral hydrogen, and this hydrogen can emit Lyman alpha photons for recombination. However, the situation is more complicated. In fact, we should consider also other cases, other mechanisms, for example, shock mechanism due to the interaction between gas and jet, collimated jet or outflows, and the cooling radiation due to radiational effects. And also, we can also introduce at least up 10 kiloparsec from the central nucleus, the resonance scattering emission. In fact, the resonance scattering processes. In fact, Lyman alpha is a resonant line, and therefore we should include the very complex radiant transfer effects, which complicates the study of the kinematics of the gas by using only the Lyman alpha profile. Very well. Therefore, by observing this emission, what we can observe is a Lyman alpha nebula. Therefore, a brief historical introduction about Lyman alpha nebulae. The first Lyman alpha nebulae were regularly detected around the high redshift radio galaxies, and here I put an example where the Lyman alpha nebula is defining black contours, is labeled in black contours, and the black colors represent radio jets. And what you can immediately see is that there is a correlation between the morphology of the Lyman alpha nebula and the direction of radio jets. In particular, what we know is that Lyman alpha profile close the radio jet emissions exhibit a very large full width Lyman alpha full width at a maximum, higher than 1,000 kilometers per second. And of course, these two points suggest that first of all, the radio jets is probably triggering this Lyman alpha emission through shock mechanism. And second point is that the interaction between radio jets and gas is disturbing this gas, providing these high dispersion values. Other interesting objects observed are the so-called enormous Lyman alpha nebulae, which usually surround multiple radio quiet quasars. And here I report two very interesting examples, like Nebula, Jackpot, and Mammoth. You can see there are different objects with the PSF subtracted. The main feature of this nebula is that they exhibit a very large, very high projected maximum projected distance, higher than 300 kiloparsec. Therefore, in this case, what we observe is not only the CGM, but also the intergalactic medium filaments, linking the high density region of the universe, in this case, the different radio quiet quasars. Very well, and the first techniques used to detect these emissions, these nebular emissions, were narrowband filters and long slit spectroscopy. However, these techniques have two fundamental problems: slit filter losses and PSF losses. The first one is due to the inability to know a priori what is the systemic redshift of the quasar, in turn of the Lyman alpha nebula. Therefore, if we have a narrowband image, we don't know if it encloses all the nebular emission. We can lose part of them. We could lose part of them. While for the PSF losses, depends on the difficulty to obtain a good modeling of the PSF of the central source, which is required to extract the nebular emission, in particular in the case in which the nebula is symmetric, in which we have a symmetrical nebula. Therefore, these two problems are probably the main reasons for which initially the detection of Lyman alpha nebula around the radio quiet quasars was very rare. With the advent of MUSE, we managed to overcome these problems. In fact, MUSE is an integral phase spectrograph with very high sensitivity, super brightness limit you see around 10 minus 80 arctosecond centimeter square per second square for only 1 hour exposure time. It has a large field of view, 1 times 1 Archimedes square. We don't have any problem about slit filter losses, and also we can produce a very good PSF modeling of the central PSF, of the central source, of the central quasar, and to have a 3D view of this nebular emission. And therefore, with the advent of MUSE, many authors started to collect Lyman alpha nebula emission surrounding radio quiet quasars, finding that about 100% of these objects exhibit a Lyman alpha nebula surrounding themselves. This is one example of a sample of Lyman alpha nebulae around radio quiet quasars by Borisov et al. And these have the following properties: Lyman alpha luminosity 10 to 43, 44, and also 45 arctoseconds. Maximum projected size larger than 50 kiloparsec. and average velocity dispersion 200-400 kilometers per second, much lower than what we observe, for example, around high-redshift radio galaxies. About my work is part of the WISH quasar project, led by the AGN group at Observatory of Rome, and it aims to study, to investigate 86 quasars obtained by cross-correlating the WISE, as not digital sky surveys, and selecting the only radio quiet and no-lensed quasars with bolometric luminosities higher than 10 to 47.2 Earth seconds, and in the redshift rate 2 to 5, and by collecting also multi-wavelength data from millimeter wavelengths to hard X-ray energies, for example, GVLA, ALMA, with GVLA, ALMA, Symphony, Muse, Chandra, etc. Here I report plot bolometric luminosities versus redshift, and I try to compare the WISH sample with other samples like Cosmos and SDSS, and you can see that we aim to study the most luminous quasars in the universe. Why? Because here we expected to find the most powerful radiative outflows and therefore the most effective radiative feedback. And in particular, the main task, the main objectives in this project are the following. Therefore, probe presence of outflows from different gas phases and at different distances from the center, from the nucleus. Constrain the properties of the central supermassive black hole and of the host galaxy, finding correlation between correlation between AGN and host galaxy, and exploring the CGM around this hyperluminous quasar, what I did. And here reports the WISH paper published so far. Therefore, okay, let me start to show you the results obtained by the analysis of the Muse data of the WISH quasar J5038. This is a quasar exhibiting bolometric luminosity 10 to 47.12 seconds and redshift 3.6. We chose it because its peculiarity. In fact, it's the only one to exhibit very powerful outflows, both at small parsec and kiloparsec scales. Therefore, after accurate data reduction and a PSF continuous subtraction of the source in the field of view by using CubeExtractor software developed by Cantalupo, what we obtain is this Lyman alpha nebula. Now, this is optimally extracted surface brightness narrowband imaging. And the Lyman alpha nebula is defined within these black T contours, while I use the T contours to show you the signal to noise ratio of 3, 5, 15, 25, and so on, estimated in the narrowband image. This nebula exhibits a maximum projected size of 150 kiloparsec and a very intense surface brightness peak south of the quasar, which that we believe it is due to the orientation of the ionization cone, which light that part, providing a lot of ionizing photons and therefore triggering intense Lyman alpha emission. In this plot, the maximum projected size versus Lyman alpha luminosity of the nebula, we compare our object, the green star, with other Lyman alpha nebulae. In particular, you see that the red circles labeled the Lyman alpha nebulae surrounding WISH quasars, therefore hyperluminous quasars. And you can immediately notice that there is not a correlation between the bolometric luminosity of the quasars and the luminosity of the Lyman alpha emission. As a very interesting result, what we obtain is a carbon-4 nebula, which is the first 3D map of a carbon-4 nebula around a radio-quiet quasar. You note that it is spatially correlated with the surface brightness peak of the Lyman alpha, and by estimating the ratio of the surface brightness radial profile for the carbon-4 and Lyman alpha emission, what we observe is that there is a constant value up to 30 kiloparsec. These 2 points are probably suggesting that the Lyman alpha carbon-4 emission are tracing the same gas and probably are triggered by the same mechanism. Therefore, this is a very interesting result in this case to explain this emission. Then we also tried to test the possible scenarios for the emission, to explain the emission of the Lyman alpha carbon-4 nebulae through shock mechanism. And we exploit shock models, shock plus precursor model by Allen et al. And Arrigoni, Battaglia et al. As you can see here in this plot, we need two helium-2 Lyman alpha ratio, carbon-4 Lyman alpha ratio, because helium-2 and carbon-4 nebula emission are the most prominent emission after the Lyman alpha detected around the high redshift radio galaxies. And we don't observe any helium-2 nebula, therefore we estimated the carbon-4 Lyman alpha ratio with different methods, finding 0.04, 0.08, and an upper limit for the helium-2 Lyman alpha ratio. And by extrapolating the models in this plot here, you can see that we have basically two scenarios. The first one in which the velocity, the shocked gas has a velocity of 250 km per second and hydrogen density 10/100 centimeters minus 3. In the second scenarios, we have a shocked gas with velocity higher than 1000 km per second and hydrogen density higher than 100 centimeters minus 3. Then, if we, the fact that we are observing carbon-4 nebula, it means that we are observing basically non-pristine gas in the CGM. Therefore, metals. These metals, you know that are produced in the interstellar medium. Therefore, we need to use some processes like, for example, radio jet, merging activity, NGN, and stellar winds to explain the presence of metals over CGM, because these processes are able to deposit metals at such scales, as I said before in the feeding and feedback cycle scenario. Well, another very interesting result is that is obtained by observing the velocity dispersion map, obtained as the second moment of the flux distribution for the only region with signal to noise higher than 3. You see here that the red colors represent the regions in which we have velocity dispersion higher than 1000 km per second. And in particular, the average velocity dispersion for the entire map returned a value of 700 km per second. By comparing our dispersion with the dispersion for other nebulae, you see that we obtained the highest dispersion never observed so far. And this is very interesting. In particular, it's interesting in the fact that we are observing this high dispersion for only Lyman alpha nebulae surrounding broad absorption line quasars. This is a suggestion that probably the AGN-driven winds can interact with the gas, perturbing the gas and providing high dispersions in these maps. Therefore, it's very interesting result. We have also other possible scenarios to perturb the gas at such large scales, as I said before, radio jet, merge activity, and winds. And here I put some example for radio jets. You see black contours representing radio jets, and this is the dispersion map. And you see that high dispersions up to 1,400 kilometers per second are placed close to the radio jets. And also for the merge activity, you see that the dispersion of the gas increase between the two merging sources. Anyway, we can exclude these two processes because, first of all, this is a radio quiet quasar. Therefore, we don't expect to observe a radio jet extended at such large scales. And the merge activity for two reasons, because we don't observe any companion in the close to the quasar, and because the gravitational effects should return values of the dispersion much lower than what we observe in this case. Therefore, stellar winds, but in particular agent winds, seems to be the most probable scenarios. And the last results confirm what I'm saying. In fact, by estimating the skewness map, the third moment of the flux distribution of the Lyman alpha nebula, which is a proxy for the asymmetry of the Lyman alpha line. In fact, for example, negative skew indicates the presence of asymmetry towards short wavelengths for the Lyman alpha, therefore presence of blue wings, if you want. And by extracting, you see that we have negative values here. And by extracting the spectrum from this region with skewing values lower than -0.5, we obtain this Lyman alpha profile. And you can see that it exhibits a broad and redshifted component relative to the systemic one, which is a clear signature for the presence of outflowing gas. And in this case, this gas is outflowing in CGM, over CGM scales. In the most simple case, it could be we estimated a velocity shift between these two peaks. Therefore, velocity shift is 1,500 km per second, a maximum velocity around 4,000 km per second, and a maximum. And these outflows, we know that we observed that reach a maximum projected size of 30 kiloparsec. Well, also in the case we should introduce, we want to introduce the complex radiating transfer effects that we suppose that we probably should include for explain the Lyman alpha profile. There are many models which describe a scenario in which there is a flowing shell that find a similar profile of the Lyman alpha. Therefore, the presence of two peaks in which the blue peak is suppressed. Therefore, also in that case, we have what we obtain is the first evidence, the first direct evidence of outflows in the CGM, of an outflow in the CGM. Therefore, to take home about this work is that we observed the first 3D map. We obtained the first 3D map of a carbon-4 nebula of metals around the radio-quiet quasar, with a maximum projected size of 75 kiloparsec and carbon-4 luminosity 10 to 43 arcseconds, comparable with the carbon-4 luminosity observed around the redshift radio galaxies. We observe multiple evidence of outflows in the CGM. In fact, these evidence are broad and blue-shifted component in the Lyman alpha profile, high velocity dispersions, and also presence of metals in the CGM. About prospective future will be useful to acquire to have deeper muse observations of these objects. First of all, to search for the possible presence of a butane in the carbon-4 profile, and also studying the morphology and the extension of the carbon-4 nebula in order to see if these metals are distributed uniform way or they are located only in south of the quasar. And then it will be important to study the properties of the outflows, like morphology or what is how the outflow properties change with the position and go on. And I think that it will be interesting also to start to see this mechanism which link the properties of the AGN and the CGM gas. Thank you.
Thank you, Andrea. We're past the hour now, but if anyone wants to ask questions, please do raise your hand, and we can do it in the video, or we'll also take questions in the chat. Okay. Rafaela?
No, actually I was clapping.
Okay.
That's clapping
That's right.
hands.
Yes, yes, yes. Okay. All right. Well, if there are no further questions, then let's thank Andrea. And so we have a speaker schedule that is, I'm going to try to share the link just so that anybody who wants to. We don't have a set schedule, but if you need to contact, yes?
Mhm.
But if you need to contact Andrea, then please look at the Google Doc that we have set up, where his email address is, and that's in the chat. Oh, wait, it's not public.
Okay.
Okay,
Thank you very much.
thank you.
Thanks everyone for joining.
Thank you.
We will hope to see you next week.
Yeah.